When you think about it, so much of our industrial world, from massive power plants to the ships that cross our oceans, runs on a surprisingly simple and honestly elegant piece of engineering. And that's the boiler. It's a machine built to do one job, and do it incredibly well. Take ordinary water, crank up the heat and pressure, and transform it into a source of pure, raw power. But how does that really happen? I mean, how do we actually take the basic physics of steam and wrestle it into something that's not only powerful, but also safe and perfectly controlled? Well, that's what we're here to do. Let's dive in and unpack the incredible engineering that makes it all tick. So here's the plan. We're going to start with the basic physics. Then we'll take a look at a boiler's vital organs and the absolutely critical safety gear. After that, we'll compare the two main designs out there, and we'll wrap up by looking at a real industrial workhorse. It all starts with a core concept that, believe it or not, you've definitely seen right in your own kitchen. Think about it. If you're boiling water in a regular open pot, it can't get any hotter than 212 degrees Fahrenheit, right? But what happens if you clamp a tight lid on it? You start building pressure. And that pressure forces the water to get way, way hotter before it can finally turn into steam. A boiler, at its heart, it's just a super engineered version of that very same pressurized pot. Now, the whole point of this is to create something called dry, saturated steam. And this isn't just the cloudy vapor you see coming off a kettle. No way. This is pure, invisible steam that's at the perfect temperature for its pressure, with 0 water droplets mixed in. Why does that matter? Because that's the state where steam is holding the absolute maximum amount of energy we can use to do actual work. And here's the amazing part. This link between pressure and temperature isn't random. It's totally predictable. There are even formulas like this one right here that map it out perfectly. Now, for an engineer, predictability is gold. It means you can dial in your energy output with incredible precision. If you need steam at exactly 338 degrees, the physics tells you that you need to generate exactly 100 pounds per square inch of pressure. No guesswork involved. It just works. Okay, so how does a boiler pull this off? How does it manage this constant, delicate dance between pressure and temperature? Well, you have to understand that a boiler isn't just one big tank. It's a whole system of brilliant components all working together in harmony. All right, let's get our bearings with this diagram of a pretty common fire tube boiler. You can see the main vessel and you can see the tubes where the fire goes through. But look at all those fittings on the outside. Every single one of them is a really clever solution to a very specific engineering challenge. So let's start with a really basic problem, visibility. You're dealing with a sealed steel drum under enormous pressure. You can't just, peek inside. So how in the world do you know how much water you've got in there? And the solution is just beautiful engineering, the water column. It's this external chamber that's connected to the boiler at the top and the bottom. And thanks to some basic physics, the water level inside this little column is always a perfect mirror of the level inside the main drum. It gives you a nice steady reading in the gauge glass, and as you can see, it's also the perfect spot to put floats that can trigger alarms if the water gets too high or, more importantly, too low. It's just a simple, fantastic solution. Okay, next problem, purity. When you boil water, all the dissolved solids and gunk get left behind. Over time, that stuff builds up as scale and sediment, and it can wreck a boiler. The answer? The blowdown valve. It's right at the lowest point of the boiler, and it lets operators periodically just blast out all that sludge, keeping the whole system clean and running right. All right, now let's get serious and talk about what is, without a doubt, the most important part of boiler design: safety. When you are containing that much raw energy, you absolutely have to engineer for failure prevention. It's priority number one. And look, you don't have to take my word for it. The source material we're looking at says it as plainly as possible. Of all the fittings on a boiler, one is the most important. And this is it, the spring-loaded safety valve. This thing is a work of art. It is not just a simple relief valve that lets off a little steam. It's engineered to pop, to snap wide open completely and instantly the second it hits its designed pressure limit. That pop action exposes a bigger area to the steam, which slams the valve open against the spring and vents pressure incredibly fast. Then, once things are back to a safe level, it snaps shut just as quick. So overpressure is one massive danger, but there's another one that's just as terrifying: a low water condition. If that water level drops and the fiery hot metal is exposed, those surfaces can overheat in seconds. They lose their strength and, boom, rupture. So you need one last line of defense. And that is the fusible plug. It's an incredibly simple yet totally brilliant failsafe. See that core? It's made of a special metal alloy that melts at a relatively low temperature. Now, as long as it's underwater, it stays cool. But if the water level drops and that plug is hit with superheated steam, poof, the core melts instantly. And that unleashes a jet of steam that makes an unmistakable, high-pitched scream, a final, desperate alarm for the operator to shut things down now.
So, we've been looking at parts that you'll find on a lot of different boilers. But the boilers themselves, they pretty much fall into one of two major design families.
And the difference sounds almost too simple, but it changes everything. It's all about what's inside the tubes. In a fire tube boiler, you have hot gases from the fire running through tubes that are surrounded by water. In a water tube boiler, you flip it. You have water running through the tubes, and the hot gases surround them from the outside. Now, that single design choice leads to a massive trade-off. Fire tube boilers, they're simpler, they're cheaper to build, and they're great for a lot of lower pressure jobs. Water tube boilers, though, can handle way higher pressures, and they can make steam a lot faster. But here's the big one. They are inherently safer. I mean, think it through. If one small tube full of water fails, it's a problem, but it's manageable. But if the entire outer shell of a fire tube boiler lets go, that is a catastrophic explosion. So to really see how all these ideas fit together in the real world, let's take a look at one of the most common, most practical designs you'll ever see, the Scotch Marine fire tube boiler. This design is an absolute workhorse. It's a favorite for all sorts of applications, from ships to big buildings. They call it a package unit because it comes as this one self-contained system. The real secret to its success is its efficiency. The hot gases from the furnace are forced to make multiple passes, 2, 3, sometimes 4, back and forth through the boiler, squeezing every last bit of heat out of them before they finally escape. And it's really that whole package of features that makes it so popular. You get that high efficiency from the multipass design, but it's all in a self-contained horizontal layout. That gives it a really compact footprint, which is perfect for places with low ceilings, like, say, the engine room of a ship. It's just a masterpiece of practical, get-the-job-done engineering.
So there we have it. We've gone all the way from the simple physics of boiling water in a pot to these complex, powerful, and safe systems that basically drive our entire industrial world. It's an amazing example of how applying fundamental principles with some really clever engineering can change everything.
But that does make you wonder, doesn't it? The core ideas we've talked about are, frankly, old. They've been around for over a century. So as we push for even more efficiency and look for new ways to generate power, what's next for steam? What's going to be the next great engineering leap in this incredibly foundational technology?